Hello, class. I want to cover the next section, which is over continuity, and this is a really important concept in Calc 1 and Calc 2. A lot of our theorems say if a function is continuous. So in order for a lot of the theory to apply, the function must first be continuous. So let's talk about what that means. So a function is continuous at a number a if the limit as x goes to a of f of x equals f of a. Now, what that means, we've talked about how to know whether the limit exists. This is saying even more. This is saying the limit must exist, but it also must be equal to the function value. And before, we had limits that existed, they might or might not be equal to the function value. So definition 1 implicitly requires three things if f is continuous at a. 1, f of a must be defined, that is, a is in the domain of f. The second one, the limit as x goes to a of f of x exists, so that means a lot. That means the left-sided limit must equal the right-sided limit, and then the limit would exist. And then the last one, the limit has to exist, and it also has to be equal to the function value at a. So, let me just draw a picture of something that's continuous, a continuous curve. Say something like this. This is f. F is continuous. Now, there's a lot of different types of continuous. It can be continuous on an interval. It can be continuous at a point. It can be continuous everywhere. It can be continuous from the right or from the left. But when we say f is continuous, we mean this is true. And so there's no holes. There's no gaps. And move this over just a little bit. And there's no vertical asymptotes. So, I know when I first learned about continuity, I think our professor said something like, you have to be able to draw it without picking up your pencil. So if you had a hole, well, actually, you might not have to pick up your pencil. If you had a gap or a vertical asymptote, you definitely would. But it's smooth, and there's no holes, no gaps, no vertical asymptotes. Let's go to the next page. And let's look at some graphs. Okay. So let's see. Let's have a function that goes through, say, 3, -2, 1, 2, 3, 1, 2. And it's got a solid dot right there, and then it just goes off and it does something. And then it also has at, I guess that is actually at 2. So that's 2. Also at 2, there's a open circle, and it does something. It does something at, let's see, 1, 2, 3, 4, 5. At 5, it has a hole at 5. And then it also has a hole at 8. And so it kind of dips down, and then it comes back, and it's got a hole right there, and then it just keeps going. Okay, so what we want to do is we want to list the values. Where, get rid of this. get rid of this, where the function is not continuous. All right. Okay, so let's see, reading from the left to the right. The first place is at x equal 2. And what's happening there is there's a gap. And the limit as x approaches 2 of f of x does not exist. So, and this is f of x over here. There's different ways that it can not be continuous, but here, the limit's not going to exist because we're not coming into the same place. The left-sided limit's coming into -2, I believe. The right-sided limit's coming into 4. So they're not coming into the same thing. Now, the next place, and so this limit does not exist. The next place is at x equal 5. Because if you look at over here, there's a hole right there at 5. So the limit oh, and I forgot to put, I need to put something right here. At 5, I need to put another point right here. Yeah. So that's actually the point 5, 4. I think. And so f of 5 equal 4. So it is defined, the function is defined at 5, but the function value is way up here. So at x equal 5, the limit as x goes to 5 of f of x, it does actually exist because if you look at it, you're coming into the same point from the left as from the right. And I think it's equal to 1 right there. But f of 5 equals 4. And these are not equal. Because the limit has to be exist, but it also has to be equal to the function value. And you'll also notice that there's a hole there. Okay, let's look at x equal 8. At x equal 8, so we're looking right here, and there is a hole there. But f of 8, in this case, does not exist. Because if you look, there is no solid dot. Where x equal 8, there is no solid dot anywhere on here. There's just a hole. So that means the function is not defined there. Now the limit can exist, but it's not continuous. So remember, saying that something is continuous is a bigger statement. I'm sorry, I can't do this. For some reason, it's like it's backwards from what I'm looking at. The limit does exist. The limit as x approaches 8 of f of x equals, I don't know, whatever that value is. It might be 1.5 or something. The limit exists. But it's not defined. So saying that f of x is continuous at a is a bigger statement than saying the limit exists. Oh, and that should be an A right there. I guess I've been using, no, it should be an X, sorry. Should be an X. So because, you know, the limit has to exist in order for it to be continuous, but even more than that, the function value has to exist and they have to be the same value. So saying it's continuous is a bigger statement. Okay, let's see what else we've got. Probably some more maps. Maybe not. Yeah. Okay, these are examples of functions that have discontinuities. Okay, here's one. F of x equal 1 over x. Now, this is what we call an infinite discontinuity. There's a vertical at x equals 0. Well, we know it's discontinuous there. There's a vertical asymptote there. And the function's not defined there. And the limit is also not defined there. Okay, so that's what we call an infinite discontinuity. And you can graph it and you can see that there is a vertical asymptote there. Now, a removable discontinuity is when you have a hole. So for example, let's say we have this function. And it's called a removable discontinuity. Okay, so we know this function is not continuous when the denominator is 0. So that's at x equal 2. So g of 2 is undefined. So we know that it can't be continuous where it's undefined. But what we can do with this, we can take the limit as x goes to 2 of the function. And then I'm going to factor the numerator, and it factors into x minus 2 times x plus 1. And then we've got x minus 2 in the denominator. And so I'm going to cross out this, because I can do that because I know at the limit x is at 2. When I'm taking a limit, x is at 2. Because normally this function is not equal to this function when I cross things out. It is when x isn't 2. But the difference is this function is not defined when x equal 2. Whereas this function, when I cross out the x minus 2, is defined at x equal 2. As a matter of fact, if I substitute in the 2, it's going to give me a 2 plus 1, which is 3. So the limit exists, but it's not continuous. So when that happens, when there's a hole, that happens. Okay, so there is a hole. Okay, and then let's look at another example. takes me a long time to get that right. This is called a jump discontinuity. And let me just draw it. So let's see at 3. It's got a hole. And then it's got the function value right here. And then like that. So this is f of x. The limit as x goes to 3 of f of x does not exist. Okay. And it's a jump discontinuity. It doesn't have a hole. I mean, there is a hole there, but it's worse than a hole. It's actually a gap or a jump. So the limit doesn't exist. You know, the function is defined at 3, but what the function value is a -1. So, but the limit doesn't exist. So you have to have the limit exist and the function be defined, and they have to be the same value. So that's what we call a jump discontinuity. And let's look at something else. Okay, we can talk about how a function is continuous or discontinuous, however you want to think about it. Here, I guess it's going to be just like I want it. Okay, that's good. A function f is continuous from the right at a number a if the limit as x goes to a with the plus sign there of f of x equal f of a. And f is continuous from the left at a if as x goes to a with the minus sign right there of f of x, if that's equal to f of a. And here's a picture of when it's actually continuous from the left. What that means is coming in from the left, you're coming into the solid dot, okay? Because, well, first of all, let's talk about f is not in general continuous. At x equal 1, there's a jump discontinuity. However, f is continuous from the left. And we can see that the limit as x approaches 1 from the left of f of x is equal to f of 1, which is 1. So the way you can remember it is, you know, if it's got the solid dot on the left, coming in from the left of this to 1, because we're going towards 1, then it's continuous from the left. If it has a dot coming in from the right, then it's continuous from the right. And if it's a function, it's not going to have 2 dots there. Okay. So what we want to do here, it says from the graph of f, and so this is f down here. State the numbers at which f is discontinuous and explain why. For each of the numbers stated in part A, determine whether f is continuous from the right or from the left or neither. So let me kind of draw this in so you can see it. There's a solid circle right there. And there is an open circle right there. There's a teeny tiny little hole right here that you can just barely see. And then over here, there is a hole. And then here, there is a solid dot. And here there is a solid dot. And then it's not defined on past, or we don't know what it does past here and here. So the discontinuities where they are at x equal -4 coming in from the left. And at x equal -4, it doesn't have a solid dot either coming in from the left or the right. So it's not continuous from the left or right. Okay, and then the next place it's not continuous is at x equal -2. And at x equal -2, it is continuous from the left, because she sees you're coming in from the left, you're coming in towards the solid dot. So it is continuous from the left. Okay, and the next place it's discontinuous is, let's see, it's at x equal 2. And then that's a hole, that's the solid dot right there. It's continuous from the right. Okay, because at x equal 2, coming into 2 from the right, you're coming into the solid dot. And then the next place there's a discontinuity is at x equal 4. And at x equal 4, it's also continuous from the right. Okay. Okay, first half is continuous on an interval if it is continuous at every number in the interval. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from either the right or continuous from the left. So let me show you a picture of a graph, and this is the graph of g of x. State the intervals on which g is continuous. So first of all, let's talk about where g is discontinuous, because we're going to need that when we write our intervals. Okay, so it's discontinuous at x equal -2, x equal 2, x equal 4, and x equals 6. Now, since nothing's going on the other side, we just consider it to not be defined there, and we don't consider it to be a discontinuity at the endpoints. Okay, so the intervals. Where g of x is continuous. And then I'm gonna decide whether it's continuous from the left or the right and show you how to write that. Give me some more. Okay, so from -4 to -2. Now, why did I put the brackets like this? Because there's a solid dot at -4 and there's an open dot in this interval. So we're talking this interval. There's an open dot at -2. Now, there's the function value. We know that's a discontinuity right there. But we're talking about, if every point in this interval is continuous. So from -4, we do include the endpoint, and then all the way up to -2. And then the next one is going to be Alexa off. For some reason I said something that made her come on. So those are both open circles. So I'm going to go from -2 to -2. There's an open circle here and an open circle here. Now, right here, there's a vertical asymptote, but notice there's a solid dot right there. So I'm going to put a square bracket and go from 2 to that vertical asymptote with a rounded bracket. And then the next point, from 4, let's see, coming on the other side of this vertical asymptote, it's continuous on this interval. And so that's going to be with an open bracket 4 and then an open bracket 6, because of course it's no point going up there, just keeps going up, up, up. And right here, that is a hole. And then the other interval is from 6 to 8. And so these are both open circles. So from 6 to 8. So, you can talk about being continuous at a point. You can talk about being continuous on an interval. You can talk about being continuous from the right or the left. And you can talk about being continuous everywhere. Let's talk about some of this. So, here's the theorem. If f and g are continuous at a and c is a constant, then the following functions are also continuous at a. So both of these functions are continuous at a. So the sum of the functions is continuous at a. The difference of the function is continuous at a. Multiplying a constant times f would be continuous at a. Also multiplying a constant times g would be continuous at a. Multiplying the two functions together, that new function would be continuous at a. And then f divided by g would be continuous at a, as long as the denominator is not 0. So as long as g of a doesn't equal 0. And then here's another theorem. Any polynomial is continuous everywhere. That is, it's continuous on all real numbers. And that's what this R means, from -infinity to infinity. And then any rational function is continuous wherever it is defined. That is, it is continuous on its domain. That's another kind of continuity. So for example, right here, if we had a rational function, well, g of -2 is not defined, because that would put 0 in the denominator. So x equal -2 is not in the domain. So we'd say g is continuous on its domain. Okay. Okay, so the following types of functions are continuous at every number in their domains. So this is an important part. It's the numbers that are in their domains. Polynomials, rational functions, which is like 1 over x. Polynomials are like f of x equal x squared plus x cubed plus 1, where you're just adding powers of x and some constants. not continents. Okay, and then root functions, which are like f of x equal the square root of x. And then, trigonometric functions like sine and cosine, inverse trigonometric functions, exponential functions, and logarithmic functions. Now, these functions are not continuous everywhere, but they're continuous on their domain. So you've got to remember that. So, I think I'm going to do an example right there. I'm going to go on a couple of more theorems. Okay, this is talking about composite functions. If f is continuous at b and the limit as x goes to a of g of x is b, then the limit as x goes to a of f of g of x is f of b. So we can just substitute in b for g of x since the limit as x goes to a of g of x is b. So in other words, you can say the limit as x goes to a of the composite f of g of x is equal to f of the limit as x goes to a of g of x. So you can just take the limit of the inside function and then whatever number you get there, then you can put it into f. Then this theorem says if g is continuous at a and f is continuous at g of a, then the composite function, and that's the little fog symbol given by fog of x equals f of g of x, is continuous at a. So let me do an example like that. Okay, so first of all, we want to know where is the following function continuous. So this function is y equal the natural log of 1 plus sine x. So my inside function is 1 plus sine x. Now this function is continuous everywhere. Because, you think about the domain of the sine function, it's all real numbers. The range isn't, but the domain is. And if you think about the curve, it's, a continuous curve without any holes in it. Now, and so here we have y equal f of g of x. So the inside is equal to the 1 plus sine x, and the outside is equal to the natural log of x. We just said the g of x is continuous everywhere. F of x, which is the natural log of x, is continuous on its domain. It's not continuous when x is negative. So this is the log function. This log function is only continuous for positive values of x. As a matter of fact, it's also not continuous at x equals 0. So f of x equals the natural log of x is continuous on 0, not including 0 to infinity. Or in other words, x greater than 0. So where is y equal natural log of 1 plus sine x continuous? Well, as long as so we've got y equal the natural log of 1 plus sine x. So what we're saying is anything that goes into the natural log function or any log function has to be positive. So that means the 1 plus sine x has to be greater than 0. So that means that sine x, so that means that sine x has to be greater than -1. So where is sine x equal to -1? Because it's not always greater than -1, because it can actually be -1. And that's when x equal 3 pi over 2, down bottom of the unit circle, down here, sign is negative 1. But then 2, anytime it goes back around the circle and it hits this point or it's this place on the circle, the sign is negative 1 again. So you have to write it like this. You have to go plus or minus 2n pi. That takes care, because 2 pi, any kind of multiple, and that should be in an integer. As long as n is an integer. As long as we go around the circle multiples of 2 pi, then we're going to end up here. So y equals natural log of 1 plus sine x is continuous except when x equals 3 pi over 2 plus or minus 2n pi. Okay, so that's a composite function. And then let's talk about the intermediate value theorem. Okay, the intermediate value theorem says, suppose that f is continuous on the closed interval from A to B. So on this closed interval, and let n be any number between f of A and f of B. Between f of A and f of B. Where f of A doesn't equal f of B. So n is, in between these two y values. Then there exists a c as an x value in between A and B, such that the function evaluated at c is n. So what it's saying is that if it's continuous from A to B, and then n is in between f of A and f of B, then there's got to be a c that, where c is the input and n is the output for this function in this interval. So basically it's saying that you cannot go from f of A to f of B without passing c, okay? Or actually without passing n. You can't go from f of A to f of B without passing n. That's what I mean. And it's kind of like, the speedometer, that's a continuous function, your speed when you're driving a car. And, you can't go from 0 miles an hour to 60 without going through all the other speeds. Your speedometer may go through them real fast, but it will go through them. So here's an example. So use the intermediate value theorem to show that the given equation has a solution, what we call a root, on the given interval. Okay. Okay, so here's the equation. Sine x equals x squared minus x. So we're saying, and here's the interval too. And this is just a theorem, that uses continuity, because up here, the theorem says, suppose that f is continuous on this closed interval. So it's not true if it's not necessarily true if it's not a continuous function. Okay, so we do this? Well, let's get 0 on one side. And then let's call that f of x, so we can talk about this as a function. Okay, f is continuous everywhere, because it's made up of sum and differences of continuous functions. That's a polynomial, and we already said that sine x is continuous everywhere. So we can use the intermediate value theorem. If it wasn't continuous on this interval, then we couldn't use this theorem. So what we're going to do is we're going to look at f of 1 and f of 2. You know, my students in class always say I go too fast, but I bet y'all aren't saying that, because I have to get everything adjusted, and there's all kinds of things for me to worry about. So f of 1 is going to be 1 squared minus 1 minus the sine of 1 equals minus the sine of 1, which you could do this on your calculator using the radian mode, of course, which is negative 0.84, which really what we care about is that it's negative. Okay, and then f of 2 is equal to 2 squared minus 2 minus sine of 2, which if you put that in on your calculator, it's about 1.1. And the point is it's positive. So will f of x equals 0 on the interval, somewhere on the interval 1, 2? And the answer is yes, by the intermediate value theorem. Because you see, you know, you think about it, it was continuous from 1 to 2, and at 1 it was negative, and at 2 it was positive. So, you know, it's doing something in here. We don't really know what. But if it's a continuous function, it can't go from here to here without passing through 0. So somewhere in this interval, it's going to be 0, because this value, f of x, is negative, and here f of x is positive. So must be 0 somewhere in between. Okay, so that takes care of that. Okay, I have a whole lot left, but let's look at a piecewise function and look at this example. Okay, find all values of a such that f is continuous on, and this should be r, which means, you know, this r means minus infinity to infinity. And here's f of x, and it is a piecewise function. So it's equal to x plus 1 if x is less than or equal to a, and it's equal to x squared if x is greater than a. So what we want to do is to be continuous at x equal a, so all of the stuff below must be true. Okay, so the limit as x approaches a from the left of f of x must be equal to the limit as x approaches a from the right, which must be equal to f of a, function value. So now the limit as x approaches a from the left, we would use this piece. So that would be equal to, if we substitute in the a into this piece, that would be a plus 1. And also f of a, because it's got the equal symbol right there, when a is equal, or when x is equal to a, it uses this piece. So that's a plus 1. Now, going the other way, the limit as x approaches a from the right, that's going to be this piece. And so that's going to be equal to a squared. Now, what we need to do then is set them equal. So what we're going to do is set this, a plus 1, equal to the a squared. So we've got a quadratic equation. Set it equal to 0. So we're trying to solve it. And it doesn't factor. So, you know, you can use the quadratic formula and just pretend like the variables x so that we don't get it mixed up with the a in the quadratic formula. So the quadratic formula goes x equal minus b plus or minus the square root of b squared minus 4ac all over 2a. And if you work that out, you'll get a equal 1 plus or minus the square root of 5 over 2. So that's what a must be, or one of those two values anyways. Okay, one more example. Okay, let me do another piecewise. Okay, so we got a piecewise function, and we want to find the numbers at which f is discontinuous, at which of these numbers is f continuous from the right, from the left, or neither. And then we're not really going to sketch it, but so, and this is, just to draw it in, x less than or equal to 1. And this one, just so you can see it, is x greater than or equal to 1. So that's where the endpoints are. So the only places, because within these pieces, this is a continuous function. This is continuous on this interval because it's only discontinuous at 0. And this is continuous as long as x is greater than or equal to 3. Now, if it's less than 3, then you're not going to, it's not defined there. So the places to look are where it changes pieces. So look at, it changes pieces at x equal 1. And then it changes pieces again at x equal 3. Okay, so at x equal 1, the limit as x approaches 1 of f of x is equal to f of 1. You need to always make sure that that's true. So it's continuous within this interval. Now, the limit as x approaches 1 from the left is equal to the limit as x approaches 1. And then you can go ahead and use this piece, and then we'll substitute in 1, which is going to be equal to 1 plus 1, which is 2. Now the limit, okay, I'm going to go out a bit so we can see all this stuff together. Now the limit as x approaches 1 from the right of f of x, we'll use the piece right here in the middle. We're approaching 1 from the right. So that's going to be 1 over x. And so that's going to be equal to 1. And, you know, I probably should have said, I should have put a minus sign right there because it's equal to 1 coming in from the left. That's because that's where the equal sign is. So f of 1 is using this piece, which would be 1 plus 1, which would be 2. So that should have said coming in from the left. Okay, so what do we have here? The limit, these are not the same values. So the limit as x approaches 1 of f of x does not exist. So it can't be continuous there. So it's not continuous because the limit has to exist. It's writing away. You can't see what I'm writing. So it's not continuous at x equal 1. Okay, we know that because the limit doesn't exist. Now, is it continuous from the left or the right? Well, if we look back up here, the way it's defined, because it's got the equal sign there, that means that this piece would get the solid dot. So it's continuous from the left. Okay, and then let's go to x equal 3. Now, let's look at the piecewise function. The limit as x approaches 3 from the left, well, we're going to use this middle piece. So it's the limit as x approaches 3 of 1 over x, which is going to be equal to 1/3. Let's see where I wrote that down. Well, anyways, so then the limit as x approaches 3 from the right of f of x, we'll use that last piece. And that's going to be equal to 0. So these are not equal. Now, what is f of 3? F of 3 would, since this has the equal under it, would be equal to 0. So it's going to be continuous from the right. Why? Because it's when you're coming into the right of 3 from numbers greater than or equal to 3, that you have the function value equal to this limit. Okay. I think that's going to be all for tonight. It's late. So, guys, I'll talk at you later. Have a good evening.